Thank you for that introduction. So yeah, definitely excited to talk to those of you here about some of work I've done during my thesis research at Yale. I won't get into too much stuff I'm doing here because, as you know, it's only been 3 weeks. Don't have much to show quite yet. But yeah, the title of my thesis was Material System Design for Predictable Shape-Morphing Robots, and that's kind of a mouthful, but I hope to show you what that means as we move forward here. And so when one conjures up an idea of a robot, it's often something like this, right? It's this rigid manipulator made of metal. It has these discrete links, joints. It's on an assembly line somewhere on a factory, manufacturing a bunch of car doors or, a bunch of the same part over and over again, sort of sequestered away from people behind these safety barriers. And while, of course, these robots have streamlined the means of production for all sort of consumer goods and revolutionized society, they don't really generalize well to other tasks than the one they're built for. I mean, this is okay. They're built for doing one thing really good. But the, I guess, takeaway here is, in general, traditional robotic design paradigms sort of have limited generalizability to changing tasks and environments. And this is just by virtue of the fact that this robot is built with fixed structures and control policies that make it just good for being at the assembly line. To take an extreme example, it couldn't dislodge itself from the assembly line, walk out the door, and then start interacting in meaningful ways with people and, in the outside world. It just doesn't have the functional structure or control policy to do so. So sort of contrary to this traditional view of robotics, my future vision looks something like this, where a robot's body, sort of represented by this generic orbular white morphology, can fluidly transition between different shapes, engage in different tasks, and navigate through different environments. Of course, this is a really, massive challenge, almost something out of science fiction. And there's a bunch of challenges associated with this, like sensing. How does the robot know where it is, given point? How does it know what shape it is? Control. How do you even go about, telling such a generic thing where to go and what to do? There's energetic concerns. Is this thing moving around? How are we going to untether it from power sources? And then there's the whole idea of shape morphing itself. So how do we develop hardware that allows the robot to change its shape to do these different tasks? And so that's where my thesis focused a lot on, this idea of shape morphing hardware. So in today's talk, I'll be discussing robots that actively change their shape for improved performance across a variety of tasks. I have this word shape highlighted here for a reason. So I consider shape change to be something like an inflating balloon, where the material on the balloon has these points and they're stretching relative to one another as you inflate it. I don't, for example, consider the rigid body rotation of a traditional manipulator, or even translation as a shape change. And you can formalize this notion a little bit if you think about like the deformation gradient and continuum mechanics. I think of a shape change as a non-trivial stretch tensor in the polar decomposition of that deformation gradient. But that's just formality. Essentially, what we're dealing with is things that inflate and are soft. So what I'll talk about today sort of focus on two tracks. The first will be a component level analysis, more fundamental material studies, where I talk to you about material systems that I've developed that allow reprogrammable shape morphing. And what that means, you'll see in a second. But to sort of supplement that perspective, I'm also going to talk about some modeling efforts. So this might be relevant to you, Greg, an inverse design for inflatables. And then I'm going to transition a little bit from these component and fundamental material studies to more systems level framework, where I'm going to introduce this ART track. You'll know what that acronym means by the end of this presentation, hopefully. And in this, we're sort of integrating these shape-changing materials into robotic systems that move around and interact with the world, and we're seeing sort of the impact that that can have. So with that, oh yeah, I forgot to say the sort of unifying theme between these two tracks of the talk is that I'm using active stiffness differentials as this mechanism or tool to program the robot's shape. And so with that, let's jump right in to the actuation track. So many of you may be familiar with the idea of a soft actuator. So unlike a traditional rigid robotic actuator like a motor. For soft robots, you use soft things. These are made of rubber or all sorts of materials that can deform, and the way that the robot can basically exert forces or move around through its environment. So state-of-the-art soft actuators can look like a lot of things, but a very canonical example is perhaps this new-net actuator, which is an inflatable here. There's sort of variants on this type of actuator where you have an inflatable internal bladder with some external stiffer material strain limiter. In this case, it's sort of this yellow plastic tubing with slits in it. You even have actuators that leverage a phase change to volumetrically expand, like this silicone elastomer with embedded ethanol. Now, this is a cool system because you can heat up the system above the ethanol's boiling point. It vaporizes inside and induces this radical expansion that can be harnessed for force output. And then, of course, there's soft actuation systems like hydrogels. And these are interesting too. When imbibed with water, they basically swell, and you can direct this swelling via programmed anisotropic materials when you're positing this material or 3D printing it. And so this is sort of like the landscape of soft actuators. But one thing I will note is everything's really operating on this principle of like swelling or volumetric expansion, pressurization, phase change, and being imbibed with water. And they're directing that with strain limiters. These are the stiffer materials on the surface to elicit some desired motion. And the sort of consequence of this framework is that all of these systems are capable of a fixed trajectory. So as a concrete example, look at the top left bending actuator. When you inflate it, all it does is bend into that shape. It can't bend, for example, in an opposite direction. It can't twist, it can't extend. This is because when it's made, they fabricate the materials and they wrap fibers around it such that they can only engage in that bending motion. And this is a fixed structure. So I see this as sort of a shortcoming with soft robotics. And if we want to step to more lifelike deformations and behaviors, we need to have a way to sort of reprogram the stiffness differential on the surface of these systems so that they can move in different ways. And so the first step I took toward this direction, I'm calling these reconfigurable laminae. The idea is pretty simple. You have this material shown in this video that's stretchy in one direction and basically really stiff in the other. And how this is made, you see this little schematic. There's basically a elastomeric matrix, which is in this case Ecoflex 30. And then you have these embedded unidirectional polyester fibers in that matrix. And then on the bottom, you have this self-adhesive layer. So what this is basically a thin layer of glue, or you can think of it as tape. So what you can do is you can take these patches with this high degree of anisotropic stiffness, and you can place them on the surface of inflating continua to govern their inflation trajectory in a very programmed manner. But we found basically by conducting uniaxial tension tests on these systems that you can really modulate the stiffness by modulating the fiber volume fraction in these laminae. So on the left graph, you see the stress strain plot, and you can see as we change color, we're decreasing fiber content. And 0 degrees just refers to sort of this axis where we're aligned with the fiber direction. So it's much stiffer, for example, than the transverse direction, which is shown in the right plot. In summary, we're actually able to achieve like a 3 order of magnitude difference in this tensile modulus between these two directions. So it's pretty significant. And so what we can do is harness this anisotropic behavior of this patch that's self-adhesive and then place it onto inflating balloons, basically. So here's basically a simple balloon. You can put it on the top, it curls up, and then you can just take it off and put it on the bottom, and it curls down. And so this is a very simple idea, but of course you can scale it up. So here are a couple of other examples of what can be done. On the top row, you have this single volumetric inflating input, which is like this sort of octopus-shaped thing. And by placing patches in certain orientations, you can elicit sort of this grasping motion or this more complex deformation mode at the top right. On the bottom row, you'll see 2 videos where I'm using patches on sort of continuum manipulators. Again, you have a single volumetric input. And by placing a couple of patches here and there at different angles, different positions, you can elicit these sinuous and very interesting curves. So it's a particular case in the bottom right. This is just a clown balloon. So your cylindrical balloon that you tie balloons, animals out of. And we'll go back and visit this because I was really interested in these shapes for a modeling problem. But what you may be thinking here is like, okay, so you kind of solve this problem of reconfigurability by having someone manually reconfigure the robot, which isn't really a solution. And I agree with you there. So the real next step I wanted to do was take the human out of the loop in that process and have the stiffnesses be able to redistribute themselves in situ without someone actually removing a patch and putting it elsewhere. And so this brought me to the idea of what I'm calling tensile jamming fibers. And so a tensile jamming fiber is, as the name implies, sort of this fibrous object that you can place on these volumetrically inflating bodies. Single fiber, it consists of a multitude of individual fibrils. So in this microscope image, you can kind of see a fiber, and then we zoom in to the fibrils. Each individual fibril then consists of this sort of hierarchical construction where we have interspersed segments of silicone, so really stretchy parts, and then polyester, so inextensible parts. So a schematic of a fibril kind of looks like this. And there's two distinct types of fibrils. There's type A and type B. And the only difference is that there's a phase offset between this inextensible polyester portion. And what you do when you make a tensile jamming fiber is you take a bunch of these fibrils with the phase offsets, put them in an envelope together. You take 10 or 15 of them. And then what you can do is use a principle called the jamming transition, which is known in the literature as a nice way to achieve high stiffness differentials by basically causing things to agglomerate and suddenly increase in their second moment of area and all these other geometric stiffness terms. But to illustrate this idea, we have at atmospheric pressure these fibrils in this sort of bounding membrane. And what I'm calling this is the unjammed state. Whoops, sorry. And then we can jam it by basically evacuating the air inside using a vacuum. So to, close to an atmosphere or 0.9, negative 0.9 atmosphere. And what happens is all the fibrils compress. They create a continuous force chain by virtue of the fact that the inextensible portions are now overlapped. And so the whole system can no longer stretch like it once did. So just to visualize this a little bit, here's a tensile jamming fiber, and I'm starting it at atmospheric pressure. So I put a 100-gram weight on it, and you can see it stretches to like 200%. But when I take the weight back off and it's elastic, it goes back to its original rest length. But when I jam the system and I put the same weight on, there's basically no deflection at all. That's because the system has jammed together, and then there it is. I release the pressure, and within a fraction of a second, it restores its original tensile stiffness. So it turns out you can actually change the extent of stiffness by just modulating the vacuum you're pulling. So if you start out at atmosphere, this is what a force displacement curve looks like. But as you increase the magnitude of that vacuum, you can get increasingly stiffer and stiffer fibers, which turns out to be a really useful thing, as you'll see in a second. But in summary, we can basically maximize this differential between the unjammed and jammed state at 20 times this stiffness, which is significant when you're dealing with these inflating bodies. And so what we can do, for example, is take this simple cylindrical inflating bladder. We pattern 3 of these jamming fibers circumferentially around it. And again, so this is one volumetric input. And we're able to basically adjust the stiffnesses on the surface to change the trajectory of this single inflating tube. So on the bottom left, you see a little key where we're showing the fibers which are jammed, stiff, or unjammed, are not stiff. And you can see we can sort of bisect the different directions by jamming pairs. And in fact, by using partial pressures, as I alluded to previously, we can achieve basically an entire hemispherical workspace with a single volumetric inflating body, which is pretty fun. And of course, you can scale this idea up too. So here's a gripper basically composed of 3 of these very simple units. You can pinch grasp a Rubik's Cube. Then you can redistribute the stiffness on those cylindrical actuators. And then I can dip the gripper inside and then basically use an inverted grasp to lift the bucket from the inside. And likewise, I can redistribute the stiffness and sort of elicit this torsional motion when I'm inflating. And then finally, redistribute the stiffness one more time using these tensile jamming fibers so that I can use a pinch grasp and lift the lid off the jar. So the idea here is we're taking, these very simple, like a one volumetric positive pressure input system, and we're able to tune the stiffness on the surface to change its trajectory to a variety of different grasp modes that are useful for robotic functions. Okay, I want to go back to the summary slide here. So I just told you about some, I guess you could say, problems with soft actuators. One of those is that they really undergo one fixed deformation trajectory. And this is sort of a roadblock, I think, to having more versatile soft robotic systems. So what I showed you was two solutions to redistribute the stiffness. One, these patches that you can sort of manually rearrange. Two, these tensile jamming fibers that allowed you to modulate stiffness in situ. And so, motivated by some of the shapes I was getting with these systems, when you have these variable stiffness patches or fibers in different locations, you can really get this wealth of interesting equilibrium shapes upon inflation, depending on where you put them, depending on their angle and all these parameters. And this really prompted me to further look into some of the more physical and mathematical aspects of how these things are inflating and how could I design these in an inverse fashion so I didn't have to be prototyping a bunch of things for one, to one end. And so that sort of took me to this phase where I was looking at inflatable design. So often when people design actuators, these soft actuators or inflatables, they'll approach design in this forward design sense in which they have design parameters like the dimensions of their actuator, the number of strain limiters, the stiffness of the strain limiters, and they're using some sort of physical model to generate a functional specification like the shape it assumes when inflated or the force it exerts. But I was more interested in this inverse approach, where you start with this functional specification, force, the shape, use a model to generate the design parameters, the number of patches you put, where you put them, these things. This can save you time, this can save you materials, and it's also just a really interesting question. And so there's been some really good work on inverse design so far in soft robotics. So there's been some work, for example, on these continuum manipulators with a single continuous, essentially, thread, and they can basically adhere it to this manipulator and change the pitch of the helix they elicit upon inflation. There's been some really cool work on inflatable characters. So given some sort of face or body shape, how can you tune, for example, like the seams of these heat sealable fabrics such that when they inflate, they closely approximate this character's face. There's been some work using reinforcement learning approaches to basically get these like inflatable membranes that pixel by pixel may be tuned with different material to inflate to this program topography. Of course, there's very classic work on McKibben actuators, artificial muscles that sort of engage in these lifelike trajectories, bending, for example, replicating the motion of a human finger. But I will remark in all of these cases, nothing really encompasses what I was interested in some of the cases I was looking at, where we had these discrete individual strain limiters along the surface distributed of these long continua. And so there really was no existing inverse design pipeline for that, which I decided to tackle. So just as a motivation, and you kind of saw this in the video at the start, just by taking these patches and sticking them on balloons, so these green circles indicate where I put the patches, you can get all sorts of really interesting shapes. There's a lot going on here. There's this dynamic process as the balloon inflates and the pressure bolt propagates through each patch. So you have this sort of dynamically evolving shape. You have the radius expanding, and then you have this elongation, multiple factors of the original length. So it's a highly nonlinear from a material standpoint, and also highly nonlinear from a geometric standpoint problem. And so this image sort of encapsulates some of those cool shapes that you can get. So to formalize this idea of inverse design for these systems, I wanted to start with for example, a 3D curve that you drew in space. So think of XYZ Cartesian space, and you draw something like this red line here. Given this target center line, what then are the output design parameters? So this is things like the number of these patches I'm placing in the balloon, their height and their width, their angle with respect to this longitudinal axis, and so forth, their circumferential position, such that when inflated, we closely match this target center line. And so the way I decided to do this was to use a two-tiered approach. The first thing I did was I looked at this target center line, and I'm using a technique which I'm dubbing kinematic segmentation algorithm. Basically, you're just using the geometry of this curve to generate guesses for what the parameters of these patches may be. And so in essence, what's happening is that we're looking at this parametric equation of this curve, R sub t, and we're calculating things called the tangent normal and binormal frames of this space curve. And these are, these exist for any space curve. You can calculate them based on the equation shown here. But essentially what it ends up being is this triad that's stuck on your curve and evolves along with the curve as it moves through space. And you can calculate useful properties from these quantities, like the curvature. This is probably a term that rings the bell. The curvature of the curve is defined as the magnitude of the derivative of this tangent frame. In the torsion of the curve, maybe a less familiar term, this basically describes a line's tendency to deviate from a plane if a curvature describes its tendency to deviate from being straight, sort of like in layman's term. But so these two parameters uniquely describe this curve, curvature and torsion. And so by running kinematic segmentation algorithm, we're basically looking for places on this line where it exceeds some tolerance curvature. And we know, okay, if it's deforming that much in that area, there must be a material there. And so that's what's sort of shown here. I'm showing this contour of a hyperbolic paraboloid, or the Pringles chip curve, which parametric equation is given there. And these little black circles sort of show you where this algorithm is thinking, okay, there needs to be some material here because it's exceeded this threshold. And here's a close-in look at what those tangent normal and binormal frames look like as the curve's moving through space. Another way to look at this is graphically. So here I'm plotting the torsion and the curvature as a function of arc length of this hyperbolic paraboloid contour. What you see is I have this dashed black line, and this is the user-defined tolerance for curvature that I have. And so anytime that orange curvature line goes above that, I'm assuming at some point along that arc length, there's a material that's inducing curvature. And so what this is providing then is not necessarily a really high fidelity solution, but sort of a seed, if you will, really coarse guess of the locations, and you can get some orientation information based on the torsion and the number of these patches. And we can use this as a seed in a more high fidelity optimization loop. And so what I'm doing in this case is I'm using a finite element analysis software. So this is Abacus, and we're basically describing this inflating balloon as some membrane elements with stiffer membrane element patches shown in purple there. And what we're minimizing in this sort of optimization is these two parameters that describe the curve, the curvature and the torsion between the target and the curve elicited in simulation. And so what this optimization loop then is allowing us to do is to tune the geometry and placement of these patches when we're now considering things like the material nonlinearity to get a really nice solution. And so practically what results are these output design parameters that we can use to make physical systems. So here's one example. On the top left, I sort of have this target curve, which is familiar. It's like a unit cell of a Hilbert space filling curve that's been a little smooth. But basically, I put this into the algorithm. I generate design parameters. I create and inflate the balloon, which you see in the middle in purple. I can 3D scan that and get a point cloud shown on the right. And then I can extract the center line of that point cloud and then sort of compare it to the target curve to see the extent of similarity. And so on the bottom graphs, you'll see curvature and torsion on the left and right, respectively, as a function of arc length. And so the red is the target curve, what we want to achieve, and the black is what we're actually achieving. And so in this case, while we're not having great quantitative similarity, I do like to point out that we're getting peaks and valleys where we want them to. So there's some qualitative resemblance, which I was excited about. And so we moved on to test this in a variety of other cases. So these are some curves that are parametrically defined, some famous curves, or ones that I literally just drew in SolidWorks 3D Sketch and then exported to see if I could match them. And so generally, again, the same holds true. We're able to match qualitatively the behavior of these curves, although not precise quantitative alignment. The tricky features to replicate are these inflection points, because the balloon really can't create these sharp changes in curvature and torsion that we see with the target curves. But this is, again, just the limitation of the materials we're working with. And so practically, what can you do with this? Okay, so we can make shapes, great, but like, what's the robotic functionality? So here's one example. We can make a balloon that's essentially a self-tying knot. So you can think a robot could use this to, on its end effector, to basically grasp itself and tie itself down to different surfaces. Could use this in vivo to, staunch blood flow or something in some medical application if you scaled this down. Which is another good thing about this. It's sort of scale invariant analysis with the geometry. The other things you can do is you can use these balloons as sort of ad hoc robotic manipulators. So here's a silly scenario where someone's put some stuff in recycling that don't belong, so you want to remove it. So we can design for specific radiuses and engage in radii and engage in different types of grasps. So we have, power grasp of small and large radii. We can grasp multiple different disparately shaped objects with hooks and curves, and then pick up these buckets for no reason at all. Okay, so that's that part. So wrapping up the actuation track, we talked about soft actuators, some reprogrammable strain limiters, sort of use that to motivate this modeling framework here. I'm going to shift gears a little bit and step from this component level view of these materials and modeling to more robotics focused view, or applying shape-changing materials to robots and seeing what can they do. So that's the arch track. So going back a little bit to future vision, one of the key elements here is that this robot's actually moving through its environment. It's engaging in locomotion. And as you saw with the previous examples, there's not much locomotion going on. There's just stuff changing shape and inflating. And so one of the things I was really looking to do is get robots to move around in the world and experiment with those. So perhaps the canonical example of a mobile robot is a legged robot. There's really awesome work in legged robots being done right now. So this is from my current lab, the RSL at ETH Zürich. Animal is this really advanced quadruped that can basically navigate all sorts of different terrains outside, indoors, really robustly. In water, there's been a lot of work too. So there's some really interesting bio-inspired design work on these efficient underwater propulsors. And so both of these robots are designed, again, just for land or just for water, respectively. There's even been some work on amphibious robots, so sort of trying to bridge that gap between land and water. And so this is a very classic platform developed by McGill back in the day, called Aqua. Basically, this hexapod-style robot has these cockroach legs to walk on land, and you can kind of remove these and then slap on some flippers, and they can swim in the water. So really cool example of an amphibious robot, but it requires someone to actually change the legs out. And so more recently, there's been works on sort of integrating these different propulsion strategies into one mechanism. So this is like the idea of a WEG or a paddle WEG. So this robot, again, has this sort of hexapod cockroach body, and it has these propellers suspended in this like wheel cage thing. So it can sort of hobble on land, and then when it gets in the water, those little paddles provide thrust for propulsion. So the same mechanism is able to be used on land and water. And so these are all great, I think, platforms. But one thing that I noticed consistently is, again, everything's using this fixed hardware. So it makes sense, I guess, for the terrestrial robot and the aquatic robot. They're just designed for those. But in the case of the amphibious robot, you could be missing up some optimal or specialized propulsion strategies by relying on one mechanism that makes compromises between the different environments. So as a specific example, this WEGS robot is really just using this paddling-based propulsion in the water, which is, rather inefficient compared to some other strategies of underwater propulsion that a lot of animals exhibit. And so the fact that all these are fixed sort of invites this idea of, okay, we can use shape-changing materials to adjust the leg shape of this robot and potentially have it specialize for multiple environments and not make any of these performance compromises. So enter the idea of amphibious robotic turtle, or ART for short. So the real idea with ART is it's this quadruped, and it has 3 degrees of freedom on each shoulder, with the kinematic mechanism shown like that. This permits us to sort of perform a range of terrestrial and aquatic gaits that are loosely inspired by turtles. I think the feature of ART that's really interesting are the limbs. And as I mentioned, these limbs have the ability to change their shape between the streamlined flipper, which is nice for swimming, and this load-bearing leg. So we're basically changing this cross-section and increasing the second moment of area so that it can support its weight under gravitational loads. And the same leg form factor, obviously would not be as effective in the water. It's not very streamlined. And so the robot can morph between these functional shapes by using a special material system. So what's being shown here, so there's a little IR video in the top right, and then this video feed here. Basically, there's a variable stiffness material that changes stiffness as a function of heat. So what you can do is heat that up with embedded heaters. Then you can inflate pneumatic actuators with this laminate, which I talked about earlier, embedded on the surface to get this program curvature distributed along the length. And then you can hold this position until the material cools, and then you can release the pressure and it will retain that configuration. It's very, very rigid when it's cold, and it's very, very compliant when it's soft. And so to get back to the flipper configuration, simply heating it up again suffices to induce stress relaxation in the material. So to make these things, I kind of alluded to that here, but basically there's 2 parts. There's this like thermoset epoxy, which is the variable stiffness material, and we embed these thin foil copper heaters inside so we can joule heat the system to change its stiffness on demand. And then the thing that's actually doing the shape morphing are these inflatable actuators, which are elastomeric actuators with the laminate bonded on their surfaces. Well, this is perhaps rather incidental, but you can tune the chemistry of the epoxy to actually maximize this differential between stiff and soft states. So it's a little interesting chemistry exercise by tuning the stoichiometry of the components. But that's sort of besides the point. But what can you do with this robot? Well, in the flipper configuration, the robot can swim underwater or on the surface of the water with different types of gaits. So on the top left, we kind of have this typical freshwater turtle gait where we're paddling. We're generating thrust with the rearward stroke and then feathering sort of as a recovery phase. The other 3 videos show this sort of figure 8 style gait that's good for submerged locomotion, and this is exhibited by a lot of sea turtles. Turns out this is way more efficient than the paddling gait because you're generating thrust through like 90% of the stroke. So you can take the same robot, you put it on land, you can morph the legs, and it can walk. Slowly, but rather efficiently. So here it is walking around Yale's campus. And so to really, I guess, evaluate the efficacy of this approach, does the shape morphing hardware confer some benefit to this robot's locomotion in different environments? We evaluated the cost of transport. And so this is a metric basically where you measure the energy expended by the robot. So in this case, we're looking at voltage times current input to all the motors. We're summing all of that to get electrical power that's consumed. And we're dividing that by the robot's mass times gravity times its forward velocity to get this dimensionless cost of transport metric, which is really useful for comparing different robots and animals across scale. So here's a plot of cost of transport on Y and then body mass of the animal or robot on the X. So ART situates itself here for sort of terrestrial locomotion, crawling and walking, and then here for swimming. And I think this is actually a good success. I was happy to see this performance because it's actually performing within the vicinity of, and in some cases outperforming these robots designed for one environment only, which is nice because our robot can transit multiple environments. So this attests, I think, some efficacy of this shape-morphing materials paradigm when used in robotics. Okay, so I want to talk a little bit about some practical problems I had with this platform for the last little part of the talk. So one of the things you might be thinking of is the actual morphing mechanism itself. How robust is that? Because it's relying on this thermal activation. And so you're correct to assume that the temperature dependence is a factor that's impacting the morphing speed and sometimes the ability to morph entirely. And so in cases where it was really cold, we're testing in January, February, in cases where the robot was, partially submerged in water and we were trying to morph it, the forced convection boundary conditions basically precluded the ability to morph entirely. So this is like kind of wake up call, like, okay, well, maybe this mechanism isn't great for like tough field robots. Second thing was robustness to mechanical failure. So the specific materials we chose, although they're very stiff and very compliant in their respective states, which was useful for shape morphing, they're brittle when they're stiff. And what happened was when we were out swimming in the, in the water, or even sometimes walking on land, we'd hit a rock and then the limb would shatter. And then, morphing would be compromised, and then I'd make another limb. And the cycle would repeat ad nauseum. I would have spent 20 hours in lab making limbs, and oh my gosh, there's a box in lab and it's just full of limbs. It looks like I'm a weird turtle hunter or something. But anyway, so the sort of solution we were thinking about for this is to use an alternative variable stiffness mechanism instead of this thermally activated epoxy. So there's this mechanism called layer jamming, not unlike fiber jamming that I talked about earlier. The idea with layer jamming is instead of these individual fibril constituents, you have layers. These can be pieces of paper, and these can be pieces of plastic, basically planar form factors. They're assembled in a stack, placed in an envelope, and are attached to a pressure source. And just like the tensile jamming fibers in atmosphere, they're free to slide relative to one another. They're not very stiff and bending. But when you pull the vacuum, the sheets agglomerate, increase the second moment of area, and you can support a lot of weight. So this paper by Narang et al. On advanced functional materials was sort of, in my mind, the watershed piece on laminar jamming. And since then, there's been some iterations. So this is the one that came from my PhD lab at Yale. So one shortcoming of layer jamming is that you can't accommodate doubly curved surfaces because we're dealing with these inextensible sheets. So if you wanted to stretch around a ball, for example, and hold that shape, you couldn't really with inextensible sheets. But stretchable layer jamming introduces this idea of these discretely interleaved units, sort of like chainmail that can stretch and then jam into that position. But the sort of benchmark test for all layer jamming systems, regardless of what they are, is this 3-point bending test. So you're applying a displacement, you're measuring a force, and you get a graph that looks something like this. So this top curve here is the jammed state when the system is very stiff, and the bottom is when it's unjammed. So you see there's a stark difference. Now this is some arbitrary set of parameters, but there's a stark difference between the jammed and unjammed states. And the jammed state can be further compartmentalized into this initial stiffness regime, this sort of transition to slip regime, and the fully slip regime. And all this means in the initial regime, the layers are remaining cohesive relative to one another. As you're pushing it down, it's acting as a solid cross-section. But once you pass a certain critical threshold force, you get a little bit of slip, sort of like a crack propagation. And as soon as that happens, your stiffness drops. So that's why the slope changes. And then eventually in the fully slip regime, you've passed the critical force, and now the sheets, as you're further displacing, are just sliding relative to one another. And basically the friction dissipation is the only thing you're seeing manifest is the stiffness. And so what I want to remark on here is we're going to use this layer jamming technology in this robot's limbs. What we don't want necessarily is to have this undesirable low stiffness behavior after a small deflection. We want to retain this initial regime as long as we can to sort of modulate between the extremes of stiffness and compliance. in the jammed and unjammed states, respectively. And so a little closer look at this will give a really interesting solution, I think. So this is the same diagram. This is the 3-point bending set for sort of a classical layer jamming system. If we look at the cross section, so this is sort of looking into the cut in the page, we have something that's into the page width B. We have a stack of n individual sheets. Each height is h thick, and so the entire height of the stack is n times h. The assembly looks something like this. So you have 15 or so of these individual pieces of paper or plastic, same dimensions. If we look at the actual expression for bending stiffness, we notice that it scales as the Young's modulus of the material times the second moment of area, which is I. And we notice one thing is that it changes between the jammed and unjammed states, this second moment of area. So for the jammed, it's I of j. For the unjammed, it's I use of j. And the exact terms are different because in the unjammed state, each of these sheets has its own neutral axis. And so effectively what you're doing is changing this stiffness as a factor of 2. So if we compute like the ratio between this jammed stiffness and unjammed stiffness, it's n squared. So what this is suggesting is basically for each additional sheet you put in the system, you're going to get n squared stiffness differentials between stiff and soft. But what I will remark is that this is not always sufficient. So here's a system with 15 sheets, like I showed in the exploded CAD view. I bend it to a desired curvature. I jam it, I hold it there. You can see it's already almost slipping, and I put a 1 kilogram weight and it just snaps back. So what's happening here is that the system is already so thick, the unjammed stiffness is so high that it's fighting that jamming force, keeping that curvature, and it wants to go back. So a little perturbation on the top would just cause it to go flat. So the observation here is that we can actually play with the math. We can augment this ratio to increase this from n squared to something higher. And the idea is if we can amplify this ratio, we can reduce this unwanted effect. So consider this example. You take the same sort of system, 3-point bending, and I start making cuts in the sheets. So these cuts are width C. We still have the overall width B, the overall height N of H. And there's some amount of material effectively removed from each cross section. So now the exploded CAD view looks something like this. I cut a bunch of material. And so the other important thing to note here is that these cuts are offset between each layer. So you don't have holes all the way through your system. What happens now when we look at the jammed and unjammed cross sections is we notice that the second moments of area become different. You have to do a little more math because you're using parallel axis theorem because of weird shapes. But essentially, when we calculate this ratio, we find that for any sort of configuration, it's always greater than n squared, which is really cool. And so this made me think, okay, what if we optimize this, start to optimize this to really maximize this ratio? So here's an example of just using the cuts. Same exact number of sheets, same exact geometry as last time, except we had introduced the cuts. I move it into position, I jam it, it retains the shape, and I put this 1 kilogram mass on it, and it holds it because of the increased geometric stiffness. So this is 36 times the weight of the specimen, which is significant. Okay, all of this to say, basically what we can do is to strategically, topologically augment our sheets in our laminar jamming system to provide this amplification of the stiffness differential. And what we find is generally the more material you remove with these cuts, the higher this stiffness amplification gets. So this plot sort of on the right is showing the normalized stiffness ratio relative to the neat sample. So you can get almost 5 times what the neat sample was able to achieve with n squared. So that's 5n squared. So effectively what this is doing is it's reducing the force required for us to bend to a shape because we have cuts, we have strain relief. We can easily bend it to a configuration. It's improving the shape retention because now when we jam it, it's not trying to snap back and it has a higher geometric stiffness under loads. And so this is perfect for a morphing limb design. And so basically we took this, we made some patterns into these laminar jamming sheets and put it into the morphing limb. So here's a video of half of the morphing limb using just neat sheets. So these are uncut. as you can see, when we inflate the actuators and jam it, not much is happening. The thing is so stiff, it just can't bend it into a position. And when we release the pressure on the outside, there's really no noticeable curvature. So our morphing is not that good. But on the other hand, when we, I'll skip ahead a little bit, when we skip to sort of what we're calling these kirigami cuts inside, when we inflate it, all of a sudden, wow, same pressure, but huge curvature difference. Jam it, and look at that, that's a nice curvature. We could probably hold some weight with that. And so that's the idea. So instead of art, now it's jart, because it's jamming art. And basically the functional difference is that we've changed these limbs, and now they're made of laminar jamming materials. They can still switch between the flipper and limb mode, only now it's environmentally independent. Doesn't matter if it's cold or hot. And now it's very fast. Within a fraction of a second, we're modulating our shape and stiffness versus last time we had all these thermal latency issues. And so what this is enabling basically is us to take the robot and do some more field testing. So here we are at a estuary near Yale's campus. And a lot of these tests we're doing, we're honestly raising more questions than they were giving any answers. So we started to realize like we're teleoperating this thing the whole time. So like, when should this robot actually like sit down and start crawling? We don't know. Like as it approaches the water, it has no sensory information to know when to do so. Likewise, when the robot's crawling out into the water, at some point it's got to change the shape of its limbs to flippers to be more efficient. But when is that? That's like undefined. We're just deciding. We're looking, oh, it's kind of in the water. When it's out there swimming around, it's being buffeted by these currents every which way. You know, we really have no ability to follow any paths. There's just too many disturbances. And so this really raised the question of like, how do we actually control it? It's got 4 flippers, which is unusual. It's like a plesiosaur or something. We're only using 2 right now, like a turtle. Anyway, interesting control problem. And then there's the whole idea when it's coming back onto land, right? At one point, should these modal transitions occur? Should it try to stand up and use the effects of buoyancy to help it get out of the water as it's walking? Or should it just slide up on the land and do a big push-up? What's more efficient? What's better? We don't know. We have to find that out. So all these sort of nebulous questions, and then I left. That was the end of my PhD. But the next generation is going to look into these. They're going to look into more autonomy, sensorizing this robot, untethering it, giving it some more ability to handle these decision-making processes for itself rather than having a human operator. So ultimately, we want to have these untethered, robust transitions. Okay, that was it. I'm going to wrap up now. But just to wrap up, so we had 2 tracks, actuation and art. In the actuation track, I'll talk about soft actuators, reprogrammable strain limiters, and some modeling work I did on inflatable balloons. The real key principles here is that we can tune stiffnesses in a very programmed way. And in doing so, we can create these sort of mechanisms that actively change shape for a desired function. And so what we saw with art was the shape-changing limb that allowed us to swim and walk with comparable efficiency to robots designed only for one environment. So, of course, this work wouldn't have been possible without my great collaborators during my PhD, many of whom are shown here, some are not. And with that, I'd like to open the floor to questions. Thank you.
Great, thank you. Cool, I think we have time for a couple of questions. Does anyone in the room have a question to start us off?
I have a few, yeah, I can throw one.
Go for it.
Specifically, so super cool stuff. Thanks for the talk.
Yeah.
For when you started talking about the curvature and the torsion, right? You were able to reduce your system to kind of just a line, right? Just your center line for the balloons. And that can be pretty difficult, I guess, as your system gets more complex. I'm wondering if you just have general strategies for trying to make that reduction in number of turns or difficulty.
Yeah, so that's a good point. So part of the reason I think that was successful was because instead of looking at the whole 3D problem from the get-go, I just collapsed it to a point and then started looking at geometry And then I use the more, high fidelity approach. So when you're dealing with arbitrary geometries, my suggestion would be, I guess, to follow a similar route. So I don't know if you're dealing with things that could be approximated as surfaces instead of space curves. But usually in my experience, a lot of soft robots can just be surfaces, right? They're kind of like thin membranes. Even if they're kind of thick, they can still kind of be a little surface, or at least have a midplane that can be described by some fundamental curvature in metric tensors. So you can start from the geometric approach there. And then I said incrementally move up in complexity. I guess that would be my approach.
Okay, yeah, that's helpful, thanks.
Thanks for sharing. I have a question
Yes.
on the jamming fibers.
Yes.
So I wonder, will the actuator rest length would affect the stiffness of the fibers, and what happens if you pump the air out after extraction?
Great. So good question. So does the actuator rest length affect the performance basically of the fibers? Is that the first part of your question? Am I understanding that correct?
Yeah.
Yeah. So absolutely it does. And so when you have a fixed geometry of fiber, if you have a really long thing you're attaching it to, that can apply some pre-tension, right? So the specific example I showed in this video, we sort of custom made the fibers for the application. And that's sort of what I had in mind, right? You have like a certain geometry of actuator, you want that to be reconfigurable. So you design them to be, at neutral length. Of course you can make these longer or shorter. So here's a cool little video. This is the co-author on the paper, Billy. And so what he has right here is basically a super long tensile jamming fiber shown in orange. And this is a very scientific video, but he's going to show you how this could potentially be used like in an exosuit or something for like some force assistance. So right now it's unjammed, it's stretchy, and he can hold this chair for a certain amount of time.
Yeah, that's cool.
But essentially, okay, he gets tired after a few seconds. But when the device is on, basically it's giving him some extra ability to hold it, and so it can hold it for much longer. So yeah, you can design them up if you'd like. The principle still holds. Remind me again of the second part of your question. I already forgot.
So my second question is how fine the resolution of your stiffness controller for the fibers?
Yep. So it's quite fine, and it depends on the resolution of whatever regulator you're using on your vacuum supply. So here's what I was talking about earlier, when I was showing this like sweeping cylinder. So basically, here's like a phase space tracking, and with a single cylinder, we can get to all these points, and we can actually further bisect these lines. So each of these lines, let's see, 1, 2, 4. So we can get, like pretty much a full hemisphere of movement. And so there's like this range though, where if you don't quite have enough pressure, you're not going to reach that viable jamming transition. So there's a sort of minimal pressure you have to get to, but then after that, if you increase and increase, you will incrementally get higher stiffness.
I see. And how do you control the pressure?
So what we did was we literally have these pressure regulators in the lab. And so some of them you can just twist the knob to change it, but some of them are like digital. So you can have an Arduino and you can have a set point, and it will just regulate it for you.
Oh, cool. Thank you.
Yeah.
All right, we have time for one more question.
I have another, if that's all right.
Yeah, go.
On this same one, you have your strain limiters, which if I understand, it's uniaxial, right? And then you attach it to this system that's undergoing biaxial expansion as you inflate it. And how do you rectify that? Are there certain design considerations to kind of bridge that gap?
Yeah, great question. So the system we put it on, let me go back to the video. Somewhere over here. Yes, this guy. So this system we actually controlled a little bit. So it's this expanding tube, but if you look closely, you can see there's fibers wrapped radially. And so this is actually preventing a lot of that circumferential expansion. And so we're really limiting it to be an extending actuator. But the principle does work for biaxial expansion. So we have a couple examples. Oh, I hope I put a video in here. We have like a membrane. Oh, I don't have it. We have basically a membrane, and we can put the fibers on top in different patterns and then change how that membrane inflates. So in this example, you basically have equal stretches in these two directions as the membrane inflates, and you can change which one to have a saddle shape or cylinder or so forth. And basically, we didn't find there to be too much of like an issue because the fibers are so like thin relative to the membrane. They don't really govern that other direction. The other thing that's playing to our favor, sort of shown by this graph, is that these fibers, when they're jammed, basically don't change in bending stiffness at all. They're only changing in tensile stiffness, which is really useful because then you can directly control that sort of metric, right? That like spacing, that linear change between points. And then we put these on things that are swelling in different directions. They're not impeding its ability to swell because they can curve with it.
Cool. Okay. Yeah, I think I can picture the saddle.
Great. Thank you so much, Robert, for coming and sharing your very interesting research with us.